Hello students, today in class 12th I will tell you about the elements of terrestrial magnetism. Terrestrial magnetism means the magnetic field of the earth. Our earth behaves like a big magnet, and it is supposed that a big magnet is kept at the center of the earth. Though there is no perfect theory to explain the magnetism of the earth, but this is true that our earth has a big magnet. Whatever be the reason, that is another thing, but our earth behaves like a magnet. And you have seen that if a magnet is suspended freely with its center of gravity, then it always stops in the north-south direction. This indicates that there must be some magnet inside the earth. Because of that, the suspended magnet always stops in the north-south direction. So towards the north of the suspended magnet, there must be the south pole of the magnet, of the earth magnet, and the south pole of the suspended magnet should be towards the north pole of the earth magnet. So, the south pole is towards the geographic north, and this north pole is towards the geographic south. So, we have the equator and the poles, and at poles, the whole of the earth, as we know that this behaves like the magnet. So, to find the Earth's magnetic field at a place three things are required, called elements of terrestrial magnet. Now these three things are the angle of declination, second is this angle of declination or magnetic declination. This is also named the magnetic declination or magnetic declination. Now second is angle of inclination or angle of dip, or magnetic dip. And the third point that we require is the horizontal component. Of Earth's magnetic field. These three things are required to know the terrestrial magnetism at a place. So now we take one by one. The angle of declination. Angle of declination or angle of or magnetic angle, magnetic declination, magnetic declination. Now we will talk about it. Now we know that there is the geographic meridian and the magnetic meridian. We know about it. It is there. These are the planes that pass through the axis. So in case of magnetic meridian, the plane that passes through the axis of the magnet and perpendicular to the plane of the magnet is called the magnetic meridian. In case of geographic meridian, this is the plane passing through the line joining the north-south direction and perpendicular to the plane of the planets, that is called the geographic meridian. So we can have like this. This is the Earth. This is the Earth. This is the north and this is south. This is east and this is west. This is the earth. This is the earth. Earth. So this is the line joining the north and south, and we draw a plane perpendicular to this plane and passing through this NS. That is called the geographic meridian. So this is now geographic meridian. This shows geographic meridian. This is geographic meridian. And the magnet is here at the center of the earth. So this is now suppose the magnet. This is now magnet. Then this is the south of this magnet and this is the north of this magnet. So this is the line, that is the axis, and then we draw a plane perpendicular to this plane of this magnet. Like this. Then this is the magnetic meridian. Magnetic meridian. Magnetic meridian. Then this is the angle. This is this so much. So this angle that is here. This is called the angle of declination. So angle between the magnetic meridian and the geographic meridian is called the angle of declination. We can also have it like this one. This is suppose the magnet. This magnet is freely suspended. This is the magnetic axis. This is suspended with this one, with the support. Then the plane like this, that's more better. We can have it like this. And then this is the magnetic axis, and we have another plane. Then you will see here that this plane, this is magnetic meridian, and this plane is geographic meridian, geographic meridian. Then this angle is called phi. This is the angle of declination. This is angle of declination. Angle of declination. So this is the magnetic field being like this. This is the horizontal component. So the angle between magnetic meridian and geographic meridian is called angle of declination. Angle of declination or magnetic declination. Magnetic declination denoted by phi. Denoted by phi. So you will see from here that this is the magnetic meridian, this is the geographic meridian, and the angle between these two, that is called the angle phi. And here also I have this one, that this plane, this is the magnetic meridian, and this plane that I have here, this is the geographic meridian, and the angle between them, this is called the declination. Declination name is given because this magnetic meridian declined with the geographic meridian. So it is declined by some angle. So because of that, this angle is given the name angle of declination. So this magnetic meridian is just below this magnetic, this geographic meridian. Otherwise, they would have coincided with each other. So they are declined at some angle. So this angle is called the angle of declination. So now we can have that at poles phi equal to 0 degree, and at equator phi equal to 90 degree. This line joining the west and east, this is the equator. So here the angle of this angle phi, that will be equal to 90 degree, and here this will be angle equal to 0 degree. So at poles the angle of declination is 0, and at the equator angle of declination is 90 degree. Now the second angle. Second is the angle of inclination. Angle of inclination or angle of dip or magnetic dip. The three names are given to this one. So now first I would like to visualize this one, the same figure as we are having here. This is the magnet. This is the magnet. This we have the magnetic axis. Then this is the magnetic field B, and this angle between them, this is theta. This is the Earth's horizontal component. This is now Earth's vertical component BV. This is the magnetic axis. Magnetic axis. Magnetic axis, and this magnetic axis is along the B, the total magnetic field of the Earth. BS, the horizontal component of the Earth magnetic field, and BV is the vertical component of the magnetic field. So the angle between the BH and B, the horizontal component, and the vertical and the total intensity of the magnetic field, this is called the angle of inclination. If a magnet is suspended freely, then this is inclined with the horizontal at some angle, and this inclination is called the angle of inclination, or the angle of dip, or the magnetic dip. So this phi, this theta. This is the angle of inclination. Angle of inclination. So if a magnetic needle is suspended freely at its center, it is inclined at some angle, with the horizontal. This angle is called angle of inclination or angle of dip denoted by theta, or we can define it that this is the angle between the horizontal component of the earth magnetic field and the total magnetic field of the earth magnetic field. It is the angle between horizontal components of Earth's magnetic field and total intensity of Earth's magnetic field. Earth's magnetic field. So this is what the theta, and you can see that at the equator, at poles, theta equal to 90 degree, and at equator, theta equal to 0 degree. So when this magnet is suspended, then it points towards the total magnetic field of the earth. So if we draw this magnetic meridian, this is our magnetic meridian. This is magnetic meridian. Magnetic So the horizontal line of this magnetic meridian, this indicates the horizontal component of the earth magnetic field. Now this can be seen that this is the angle of meridian. This. So now here we have at poles theta equal to your 90 degree, and at equator this theta equal to 0 degree. So this B, this is now total magnetic field, and now we can have relation. Now third thing that we have the horizontal component of the earth magnetic field. The horizontal line in magnetic meridian shows horizontal component horizontal component of Earth's magnetic field. Earth's magnetic field. Magnetic field. So let's now from this triangle let BH equal to horizontal component of Earth's magnetic field and BV the vertical component of Earth's magnetic field. Then you can see that the vertical component is always vertically downward and horizontal component is along the equator. So now we have this clearly this BH is equal to B cos theta and BV equal to V sin theta. This is a vertical component. So at the poles the magnetic field is vertically downward and at the equator this is along the line of the along the equator. So just you see that if we divide by these two, now it gives B equal to square root of BH square plus BV square. And tan theta is equal to BV upon BH, or we can have theta equal to tan inverse BV upon BH. This is now total magnetic field and this is the angle of inclination. And you can see from here that if BH equal to BV means both the components are equal, then B equal to BH root 2 and theta equal to 45 degree. So when both the horizontal component and vertical components are equal, then this total magnetic field is equal to the root 2 times of the horizontal component of the Earth's magnetic field, and at that place the angle of inclination will be equal to 45 degree. So this, with the help of this theta, that we have the knowledge of this one, we can have a relation between VV and PH. Suppose this tan theta is given to be 30 degree, then the tan 30 equal to 1 upon root 3. So this BV upon BH equal to 1 upon root 3. So if we have this theta equal to 30 degree, then tan 30 equal to BV upon BH. So this is now 1 upon root 3. This is now BV upon BH. So this BH equal to root 3 BV. Now in that condition we can have the relation this B. Now B equal to square root of, in place of BH we write down this one, root 3 BV. This is now whole square plus BV square. So if you calculate the root 3 square means 3 plus 1 4, so this is now 2. So this is now 2BV. This is equal to B. So much. So if we have the knowledge of angle object, we can find the horizontal component and the vertical component of the Earth's magnetic field. And this you always remember that at the poles the magnetic field is vertically downward and at the equator it is perfectly horizontal. At poles of Earth, there is only vertical component. Vertical component BV and BH, this is equal to 0. This is equal to 0. So when this BH is equal to 0, then tan theta is equal to infinite, so theta equal to 90 degree. So you can see that tan theta is equal to BV upon BH. So BH equal to 0. So this is equal to infinity. This is not tan theta. So theta equal to 90 degree. And at the poles we are having only the vertical component, no horizontal component at all. So the magnetic needle becomes perpendicular. If you carry the magnetic needle there, then this will be just perpendicular. And at the north pole, the south of the magnet will be perpendicular. Or at the north pole, the north will be just perpendicular. So magnet will be like this one. Magnet. This is now magnet. Then this is suppose this is now Earth, and this is now Earth. This is now north, and this is now south. Then here this is the north, so this will be the north pole. Just vertical downward in this way. And in south, if we are having at south, then the magnetic will be like this. This is now south pole, this is now north, like this. So at the poles, the magnet is vertically downward. At the north is vertically downward, and at south is vertically downward. And at equator, there is only horizontal component. Horizontal component BH and BV. Horizontal component and BV, the vertical component is 0, BV equal to 0. So what we have, that if we have this tan theta is equal to BV upon BH. Then BV is equal to 0 upon BH. This is now tan theta. So theta equal to 0 degree. So theta equal to 0 degree. So this is at the equator. So at equator there is only the horizontal component and vertical component is 0. So this tan theta and theta equal to comes out to be not 0. So this is what that at the poles this is 90 degree and at equator this is 0 degree. So we are having the two components of the Earth's magnetic field. So this is about the terrestrial magnetism. Its elements required to know the value of the horizontal component at certain place. So at different places the angle of inclination is different and the vertical and horizontal components are also different. So this is the elements of terrestrial magnetism. Thank you very much.